My name is Dr. C. Mahender. I'm working in assistant professor in Institute of Aeronautical Engineering College. Okay, today my topic. Actually, in the last class we have seen uh, what are uh, what are the nanomaterials. What is the definition of nanomaterials, and what are the synthesis methods of nanomaterials. Today my topic is today we'll see a flame synthesis of nano titanium dioxide and its application. So today we are going to see a flame synthesis method. So flame synthesis is one of the method to synthesize the nanoparticles. Okay. So we'll see what is a flame synthesis, and in the flame synthesis, I will explain how the titanium dioxide is synthesized and what are the various methods are available for synthesis of titanium dioxide also. Okay. So we'll see first objectives of today lecture is synthesis routes of nanomaterials, flame synthesis method. Today I will give a brief introduction about the flame synthesis. Flame synthesis, we know that flame synthesis is a novel method to synthesize the nanomaterials, which are very easy method to synthesize nanomaterials. Okay, and in that I will explain how we'll synthesize the titanium dioxide. Okay, I will explain how we'll synthesize the titanium dioxide, and also I will explain its application in advanced oxidation process to degrade organic pollutants. So these are the objectives of today lecture. Okay, synthesis routes of nanomaterials, flame synthesis method introduction, synthesis of titanium dioxide, its application in advanced oxidation process to degrade organic pollutants. What is a flame synthesis method? Okay, flame synthesis method is one of the method to synthesize the nanomaterials. Okay, this process is also called combustion method. This method is also called as the combustion method. So this is a flame synthesis method. So we can see from this one. So this is a method in which we'll use one fuel and one oxidant and the precursor material. Okay, so fuel will be common in all the cases, and oxidant will be the common, and uh, from this place we send the precursor catalyst. So in this method, precursor catalyst means it will be source of the nanomaterials. This is a combustion method. So why this is called combustion method means, in this method, first we'll take flame. First we'll take the flame with the help of any fuel, like hydrogen or the methane or LPG. Any hydrocarbon fuel will take, and will take oxidant as oxygen or air. So any oxygen source we can take, air or oxygen, and we'll take in the precursor gas. In the precursor means, suppose if we want to synthesize titanium dioxide, so we have to take titanium tetraisopropoxide as a precursor. If we want to synthesize nickel, we can take any nickel based precursor. Okay, so this method is a very simple method to synthesize the nanomaterials. Okay, what will happen in the flame synthesis of nanomaterials? What will happen when we compare to the sol gel method and CVD method? In all the methods of synthesis of nanomaterials, this method is very easy method, and it does not require any purification. Without the purification, the material which we synthesize from this process will be used directly without any purification techniques. Only after the synthesis of the nanomaterials, we go for the calcination. That calcination is also to remove any amorphous particles, amorphous particles. So flame synthesis is a method In this method, we can also synthesize the carbon nanomaterials, carbon nanotubes, and carbon nanomaterials also can be synthesized, and the metal doped carbon doped nanometals also can be synthesized. Only what we have to do, this first I will explain what it contains, the flame synthesis method. So flame synthesis method contains, so this what we are seeing, this is a flame which will be generated. Flame will be generated by combustion of the fuel. So here fuel may be the hydrogen, or it can be take methane, or it can be take acetylene. So any, this may be hydrocarbon gas, this may be hydrocarbon gas, and from the oxygen this may be air or oxygen. Oxygen will be used as oxidant. This will be used as oxidant, and this will be used as a fuel. And here the precursor one. And here the precursor, from the precursor, if we want to use a titanium dioxide, so we have to take the titanium dioxide and we have to dissolve, we have to take the titanium in suitable solvent. In suitable solvent. Okay. Suppose if you want to synthesize the titanium dioxide, titanium tetraisopropoxide can be taken as directly, so directly, and it can be sent into the flame. Okay. Okay, students. Okay, we this is a flame synthesis method. So what is a flame synthesis method in this one? What it contain? So from the fuel side, there is a three concentric pipes like this. There will be three concentric pipe like this. So from the middle one, there is a flame, and in the middle one, precursor, and from this one may be the fuel. This is our, okay. So this is a flame synthesis method. Uh, from this one, we'll send the fuel. From this one, we'll send the oxygen. From here, we'll send the oxygen. First, we are going to talk about what are the advantages. So, what are the advantages of the fuel cell? Yes. So this is a method. So first, I'll discuss about a comparison of flame synthesis with other methods. So what is the advantages of the flame synthesis method is, suppose we'll take here, this is our precursor material. So I will explain about how the platinum doped aluminum oxide will be synthesized. So in this one precursor, we'll take first, this route. So now the route which we are seeing is, so first we'll discuss about this platinum precursor will be taken, and precursor will be dissolved in a suitable solvent. Precursor will be dissolved in a suitable solvent, and it will be injected in a flame. It will be injected in a flame so that the solvent will be organic, so easily it can be easily evaporated, and directly we can collect the platinum doped aluminum particles. So from this one, we'll take the platinum doped aluminum particles, and here from this one, suppose if we see this method, aluminum precursor and mixing, and this is a precursor solution and precipitation. After the precipitation, we have to go for the washing, and then we have to make the platinum and aluminum slurry, and mixing, and uh, and mixing and mixing aluminum from this side, and again we'll take the platinum precursor, and we'll the mix, and we are mixing the platinum doped aluminum from this side. So there are two ways. So directly we'll take the precursor here, and we'll mix in a suitable solution, and from this side, platinum will be taken in a suitable solvent, and platinum and the aluminum mixed here both, and it will be it will be synthesized. So we can see, first we'll see the synthetic route method. You can see there are two methods. So first we'll take in the first I will discuss the flame synthesis method. First we'll take the aluminum precursor, right? Aluminum precursor. This is a aluminum precursor. From this one we'll take the platinum, and both will be mixed in this precursor, and directly that will be sent. This is flame. This will be flame. Platinum and aluminum. Platinum and aluminum will be mixed in a flame, mixed in a one precursor, and that will be injected in the flame. And in the injection in the flame, the solvent will be evaporated and the particles will be collected here. So we'll get the platinum doped aluminum catalyst here. So directly we'll get. Suppose in the next case we'll see precursor material first will mix in the solution, and it will be undergone for precipitation, and after the precipitation, filtering, washing and calcination, then it is a mixed in a slurry of platinum. So here precursor platinum will be coming from this side. Again the platinum will be mixed in this one. After this impregation or precipitation, wet platinum Al2O3, drying and calcination, and finally this is a product. Finally, this is a product from sol gel method. This is a product from sol gel method. This is from flame synthesis method. So we can see in the second step, right side is the sol gel method. This is called sol gel method. This is sol gel method, and from the left side it is a flame synthesis method. Okay, so we can see we can avoid all these steps. What steps we can avoid from the what steps we can avoid from the flame synthesis method? Flame synthesis method directly synthesize the nanomaterials. Suppose if you want to synthesize a nickel, so nickel can be dissolved in a suitable solvent and directly injected into the flame. We can collect the nanoparticles. So in suppose if we take the same procedure, same nickel nanoparticles has to be synthesized in the sol gel method. So we have to synthesize in several steps. So that one, first one we have to mix in a suitable solvent, then we have to go for precipitation, then we have to go for the filtration, then we have to go for washing, then we have to integration or precipitation, then drying, and then calcination. So we can avoid the four steps. We can avoid the four steps in the flame synthesis. So that's why flame synthesis method is a very convenient method when compared to the sol gel method, and it is a one-step mechanism. So we can say simply flame synthesis is a one-step mechanism, whereas the sol gel method, it will take several steps for synthesizing of nanomaterials. Okay. So combustion process. Okay, combustion process are used in industry for the large scale production of powders such as silica, titanium, and carbon black. So any nanomaterials can be synthesized, but the familiar methods are the familiar materials which used by the synthesis of flame synthesis is silica, titanium, and carbon black. From the above literature mentioned, so I will see some of the literature who has synthesized the nanomaterials. So S.E. Praxinis et al. 2002 aerosol science. So this process is called flame spray pyrolysis. So they used methane as fuel and oxygen as oxidant, and they synthesized this silicon dioxide, and the production rate is 9 grams per hour. So per hour 9 grams it can be synthesized, and the main criteria in the synthesis of nanomaterials is the specific area, the specific surface area. So the specific area of the product ranged from 391 to 900 meters square per gram. So Praxinis et al. Synthesized the silicon dioxide in 2002, and he got the 391 to 70 meters per gram. And in the second one, He Dong Jong et al. 2001 Material Research Bulletin. It is published in Material Research Bulletin 2001. Diffusion flame reactor. So he synthesized. You can see he synthesized argon. So what is the argon? And what is the important thing here? Uh, Along with the fuel and the oxidant, they continuously they will use some inert gas. So in this method, inert gas will be used as nitrogen or the argon. So in this method, so he used argon as a inert gas. Okay, use argon as inert gas. Okay, okay. So argon will be used as inert gas. He used inert gas as argon, and titanium chloride TiCl4 as precursor material precursor material, and as a hydrogen as a fuel. He used the air as a oxidant, and hydrogen as a fuel, and argon as inert gas, and air as an accident. So a flame characteristics of the diffusion flame reactor has been investigated to synthesize TiO2 range. So we got the nanoparticles range of up to 10 to 30 nanometers. Up to up to 10 to 30 nanometers. Okay. So now Sotis E. Praxinis 2001 Combustion and Flame. In 2001, he synthesized, he took methane and oxygen, fuel as a methane and oxygen as accident with oxidation of titanium tetrapropoxide. So you have taken precursor as TTIP, and fuel. This one will be taken as fuel, and it will be taken as oxidant, and he reported the average primary particles as increases with the flame temperature decreases as increasing distance from the burner. So in the flame synthesis method, so many people has been investigated in so many times. So some people has been taken methane, some people has been taken hydrogen, some people has been reported with LPG, and there are also variation between the inert gas also. Some people has been reported about the nitrogen, some people has been taken the argon gas as a inert gases. And precursor material will be depending upon, suppose if you want to synthesize the titanium dioxide, so they have been taken titanium tetrapropoxide or titanium chloride also they have taken. So hence, uh, in this experiment, LPG is used as a fuel, and oxygen will be used as an oxidant, and titanium tetrapropoxide will be used as a precursor. Okay, so we can see what is the mechanism. So what is the mechanism, and how the particles will be formed in this one. I'll explain. So from this one, this is a powder. So finally we got the powder, and uh, you can see this mechanism has been explained by Sotis E. Praxinis mechanism in 1997. In 1997, he explained how the particles are formed in the flame synthesis method. So you can see, I also explained in the flame synthesis method, the precursor material are get vaporized. That vapor are injected into the flame. In the flame, the particles has been synthesized. So this type of particle synthesis is also called as bottom-up approach. So bottom-up approach means directly we are converting the materials into the nanomaterials. Okay, so the flame synthesis mechanism has been explained by the Sotis E. Praxinis in 1997, how the particles are forming into powders. So first you can see these are vapors. So from where these vapors we are getting? These vapors are from the precursor. So precursor, we are first in the first step, what we are doing, we are taking the precursor, and precursor is dissolving suitable solvent, and that suitable solvent are converted into the vapors. That vapors are injecting into the flame. These vapors are injecting into the flame. Okay, so you see these vapors are injecting into the flame. Then chemical reaction or collision or controlled nucleation coagulation. So after this one, chemical reaction and collision controlled nucleation coagulation, and it is forming the particles. These particles is directly converting into the powder. The vapors are directly converting into the powders in the flame synthesis method. Suppose if we take heat, or suppose if you take the right side, so these are the solids are heating, that chemical reaction is taking place, and collision, control, nucleation and coagulation will take place. And again the heating, the molecules are the clusters. These molecules are clusters. If we go for the condensation, evaporation or controlled nucleation, there is a particle formation will be there. After this particle formation, a surface reaction will be taking place, and coagulation and aggregation with the precursor will take place, and there is a formation of fine. This is a final product. This is a final product. So these are final products. So we observed in the flame synthesis method. Okay. So this mechanism has been explained by the Praxis E in 2007. So yes, so these are the some sim XRD images. So we can see in titanium dioxide. So in titanium dioxide, so there is a anatase phase and rutile phase and brucite. So we know that in titanium nanoparticles, so we have anatase phase, brucite phase, and we have anatase phase, okay, rutile phase, rutile and brucite. Okay, so this is the anatase phase and this is the rutile phase. So we can see here also the rutile phase, anatase phase, rutile phase. So we can see the synthesis of nanomaterials when we have taken LPG of 0.4 SLPM. So we got the anatase phase is maximum. So this sharp peak indicates in the XRD. So these three are XRD reports. So we can see this sharp peak. Where this sharp peak indicates that our particle will be in a crystalline form, or our particle will be in a nano form. So this is also so we are not seeing any brucite phase here. So this is the advantage of the flame synthesis, that in the flame synthesis we expect 99.99% will get the uh, will get nanoparticles only, and that will be very crystalline. And only the thing is we are not observed. We can see from this XRD data there is no formation of the brucite, even though if some amount of the brucite phase is formed, that can be removed by the calcination. Okay, okay, students. We know that titanium dioxide has three phases: anatase phase, rutile phase, and brucite phase. So anatase phase is more active when compared to the rutile phase, and brucite phase is least active when compared to the rutile phase. So anatase phase will be considered as highly crystalline and highly active when compared to the rutile and brucite phase. So in the flame synthesis method, we can expect the 80% of the sample will be anatase phase, and remaining 15% will be brucite, and the remaining 5% will be the rutile phase. Okay, so the advantage of the flame synthesis method is we can synthesize the particles instantly, and this process is called one step mechanism and one step process, and it does not require any purification other than the calcination. So even calcination also does not require in some cases. This is a flowchart diagram of flame synthesis. Okay, these are the some. So next class we'll see. So these are the references I have taken from this: The Essentials of Nanochemistry by N. Kumar, Introduction to Nanoscience and Nanomaterials by Dinesh C. Agarwal, and An Introduction to Nanomaterials and Nanoscience by Asim Das, CVS Publications and Distributions Private Limited. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.